Welcome to Server Logic Simplified.
Have you ever experienced a critical application suddenly becoming unavailable, leaving users frustrated and operations stalled? What if there was a robust way to prevent such disruptions and ensure continuous service? Yes, absolutely. Software redundancy significantly improves application resilience by ensuring continuous operation even when individual components fail. Resilience in this context means the ability of a system to recover from failures and continue to function, often without any noticeable impact to the user. The core mechanism behind this improvement is the elimination of single points of failure. By having multiple identical instances of software components or data, the system can transparently switch to a healthy backup if one fails. This principle applies across various layers of an application. For instance, in an active-passive setup, one component is running and serving requests while another identical component is on standby, ready to take over. In an active-active configuration, multiple components are simultaneously processing requests, with load distribution handled by a load balancer. This not only provides fault tolerance against hardware failures, but also protects against software bugs, unexpected restarts, or even network segmentation issues affecting a specific instance. Database replication is another prime example, where data is copied across multiple servers, ensuring data availability and consistency even if a primary database becomes inaccessible. To implement software redundancy effectively, you would typically start by identifying critical components in your application architecture. For stateless application servers, this often involves running multiple instances behind a load balancer. If one instance crashes, the load balancer simply routes traffic to the remaining healthy ones. For stateful services like databases, techniques such as master replica replication or sharding across multiple database clusters are common. Message queuing systems also employ clustering to ensure messages are not lost and processing continues even if a node goes down. When designing for redundancy, it is important to consider the complexity it introduces, as well as the associated operational overhead and resource costs. Beyond simply having backups, advanced redundancy strategies leverage patterns like the circuit breaker. A circuit breaker pattern prevents cascading failures by stopping requests to a failing service instead of overwhelming it, allowing it to recover. Similarly, well-implemented retry mechanisms with exponential backoff can complement redundancy by gracefully handling transient issues. These sophisticated approaches contribute to a system that can not only survive individual component failures, but also gracefully degrade and self-heal, a key characteristic of highly resilient distributed systems. This design also facilitates zero-downtime deployments, where new versions of software can be rolled out without interrupting service, as traffic can be gradually shifted from old to new instances. Embracing software redundancy moves your application from a fragile single point of failure to a robust, continuously available service. By strategically duplicating components and data, you ensure your users experience uninterrupted service, safeguard business operations against unforeseen disruptions, and ultimately reduce the significant financial and reputational risks associated with system outages. This proactive approach to system design is fundamental for building modern, dependable applications that meet today's demanding reliability expectations.
If this helps you code smarter, like, subscribe, and stay tuned for more.